um, a bar chart that looks like this. That's horrible. Like that to me is like the worst class to teach because, like I said, you've got everybody like over here is like, let's go, come on, challenge me a little more, come on. And then people over here are like, whoa, wait, I'm sinking, you know? So this is like an upside down bell curve where what we're looking for is more like a standard normal distribution, which would be, that's not standard normal, but it's, you know, it's better than that. So I'm encouraged. I think a lot of people have put themselves in a decent position to still get an A or a B in the class. And we have to just keep going, okay? Yeah, we ready? Any questions or concerns or comments? I was asked about, do I drop a test and do I replace a lowest test with a final? And that was another thing that student was asking me, you know, can you know, whatever. And I'll say this, I mean, in the syllabus, on paper, no, okay? And in fact, we have a departmental policy that we're not supposed to replace tests, all right? That's just a departmental thing. Now, if you got, 60, 50, 40, 30, if you were in this group right here, and trust me, I would never offer anything to one student that I don't offer to everybody, okay? But if you're in this category here, and you, on the next tests, you're over here on exam 2, and on exam 3, and on the final, then I think we have some sort of grounds for maybe saying, hey, this was an anomaly, okay? You got it together, you changed your study habits, whatever it was, and maybe we can make it so that this doesn't like completely destroy your grade, okay? But I'm not gonna even have that conversation until I see exam 2, exam 3, and the final. And then after the final, you can talk to me about it, all right? And that would go for everyone, all right? If you're over here and you just do that exam 2, 3, 4, and in the final, then you don't need to really talk to me about anything because you're gonna get an A. I'm just talking about, I'm not gonna let this, one bad test prevent you from passing the class. Does that make sense? I should probably restate that. I'm not gonna let exam 1 prevent you from passing the class because to do well on exam 2, this material, you have to know it. So if you do well on exam 2, that means between now and exam 2, you kind of figured it all out. You pulled it all together, okay? So, all right. Anything else? Lewis? John Avila. Okay, there we go. Hold on. What's your last name? Did I miss it? Lewis? Adam?
Yes, sir.
No, the other Adam. Okay. All right. I hope that you felt the test was fair. We won't have that conversation. All right, here we go. So we move on. Y'all feeling okay? All right. We're going to move into 6.2. 6.2 is called trigonometric integrals and substitutions. Hey, by the way, did y'all study in groups? I know you were trying to get a group together. Were you able to?
I wasn't able to.
No?
I had to go to a little bit.
Yeah, a little bit groups. Okay, I really am wanting to encourage you to get into groups. I don't want to have to offer bonus points to make you study in groups, and I know some of you can't study in groups. But I really do think that there is a value in getting together with other students. And so, if you do study with some other students, please do keep a log of who's there and what date you met and who is in the group, okay? And then give it to me like they just did. Just because this may help you at some point, all right? I'm not going to say it's a bonus, but if you're sitting there and you need 2 points to get a B, and I see that you were on these groups, I'm going to consider that more than if you never did that, all right?
Can we bring in, I know I have people up here I'm studying with, and we're not keeping track of it.
Start keeping track.
Start keeping track?
Yeah.
So a printout of the hours in the lab wouldn't be sufficient?
Well, I just want to see a piece of paper of the people who were there on the day, and just for every day y'all meet, just keep a log.
Okay.
Yeah.
Yes, sir.
Okay, chapter 6, section 2. This is a monster section. It's a long section. There's a lot of material in here, okay? And fortunately for us, it's going to be broken up into two days of lecture. In the first day, we're going to be covering, that's today, what are called trigonometric integrals. And those are going to be integrals that involve trig functions. So we're going to see like sines, cosines, tangents, secants, things like that. And then after that, we're going to be doing what's called trigonometric substitutions, which we'll call trig sub. Okay, so we have like u sub, which is our basic substitution we've already learned. Now we're going to have something called trig sub. So to do trig sub, all right, to do this, you have to be able to do this, because to do trig sub, we're going to take a problem and we're going to do some weird stuff to it, and then when we're done, we're going to be looking at a trig integral, and then we do what we need to do, which is what we're going to learn today. So can't do this if you don't know how to do that. All right, so let's talk about trig integrals. There are some things we already know how to do. Let me try and make this a little bit bigger. Yeah, that'll work. So some things we already know, right? Obviously, we know the antiderivative of sine of x is negative cosine of x plus a constant. Antiderivative of cosine of x is sine x plus a constant, right? This is all, we've got this. I'm assuming that. All right, now this one was something we covered in class. I think I did ax plus b in here instead, but you could say that if it was just ax, that's still a linear expression. The antiderivative, we have to compensate for that a by scaling out by 1 over a, right? And then if it's sine here, we're going to have a negative. If it's cosine, we don't have to worry about the negative. So that we did, right? So now we need to see if we can come up with some sort of strategy for attacking integrals that have, let's start with just sine and cosine in them. And then there's a set of steps. It says if we are presented with an integral involving powers of sine and cosine, we can attempt using the following strategy. And there's part 1, then there's part 2 that continues on the next page, and then there's a part 3. And I'm not going to read those because if I read them, you're going to be like, huh? So what I'm going to do instead is I'm going to do some examples, and you'll see, then we'll go back and look at the strategies, and I think the strategies will make a little more sense after we do the example. So I'm going to start with this first one, integral sine cubed of 4t dt. Okay, now do you remember that I showed you that power reduction formula? Do I remember that? I proved to you that we can do sine to the n of x dx. All right, that is in the book, but it's not on your formula sheets, and on a test you can't use this power reduction formula. So if you see this problem on a test, you must do it the way I'm about to do it. All right? So I'm just saying that because you might be saying, hey, can't we use that formula? Technically, yes, but you don't have it during the test, so you can't. So here's what we're going to do. The strategy here is this. Because it is an odd power, you see this is an odd power of sine, I'm going to factor out one sine. Or not really factor, I'm just going to rewrite it so that I've split up the factors as sine squared 4t times sine 4t dt. So that's just some algebra, right? Now the reason I'm doing that is because this right here, sine 4t dt, is the derivative of what? Of a cosine of 4t, right? Now we're off by constants and things like that, but would you agree that if I look at this, that could be the derivative of cosine, yes? Mm-hmm. And this sine squared can be rewritten using a Pythagorean identity. So we're going to rely heavily on the Pythagorean identity today. So if you don't remember well, you better remember the Pythagorean identity, but I will remind you of the Pythagorean identity. That's it, right, from pre-cal. And the way this identity works is that you can solve for either sine squared or cosine squared. So if I wanted to solve for sine squared, it would be 1 minus cosine squared, right? And if I solve for cosine squared, it's 1 minus sine squared, right? So I can do either one, doesn't matter. So because this is an even power of sine, right, squared, I could use this one right here and rewrite it in terms of cosine. And that's a good thing because we just said that this is the derivative of cosine, isn't it? So what we're going to have here is like a basic substitution. In here we're going to have cosine, that's going to be our u, and then when we take the derivative of it, it's already going to be sitting here, but it's going to be off a little bit, okay? So I rewrite this now, integral, this becomes what? I need it in parentheses. 1 minus cosine squared 4t. Good, all right. And then sine 4t dt, like that. So that's the same problem, right? All I've done is just use some identities from pre-cal. That's all I've done, right? And now, yes?
I was about to, never mind. I was going to ask you, you're going to make the sign U, right?
No, I'm not going to make the sine u. Why am I not going to make the sine u? What would the derivative of that be? If you make the u sine, the derivative would be cosine, right?
Yeah.
And that cosine is trapped inside a parentheses with a squared. It's not like out by itself. This is the thing that's out by itself, right?
That's what I was saying. I was saying that the sign outside of it, the sign 4t,
Is not going to be the u. It's going to be du.
because you're going backwards.
I'm not going backwards. I'm using basic substitution,
Yeah.
right? I just, by peeling off that sign, I'm recognizing that if I let u be cosine, here's its
You'll get
derivative.
sine.
That's right.
Yeah.
But you said let u be sine.
bad.
Okay, so I just want to be clear on the language there.
Yeah.
Okay, so what I'm going to do is I'm going to let u be
Cosine.
cosine of 4t, and then du will be, well, we have to use chain rule, and there's a negative that pops out, because we're taking the derivative here, right? Not antiderivative.
Yeah.
The derivative of this is negative 4 sine 4t dt, right? That's our derivative. So at this point right here, I'm using u, that's a u, that's terrible. I'm using u sub right here, right? U substitution. And I'm trying to match things up. I've got sine 4t dt right there, right? That matches this. So I'm going to have to scale both sides by a negative 1/4, right? Multiply both sides by negative 1/4. So negative 1/4 du equals sine 4t dt. So now I've got a perfect match, right? This right here will be replaced with 1/4 du. And now I just have to go back and look at the rest of the integral and see what to do with this. So this will become 1 minus, now this is u squared, right? This is u squared. Cosine of 4t is u. So u squared. And then I had negative 1/4. I should have pulled that out. Let me give myself a little more room here. Negative 1/4 comes out, and then du here. That makes sense? And now, at this point, this is just, what? How do you integrate that? Just power rule, right? I mean, what's the antiderivative of 1? X, but our variable here is u. So the antiderivative of 1 right now is going to be u. The antiderivative of u squared is going to be 1/3 u cubed, right? And I'm going to have a negative 1/4 in front of all that. So negative 1/4, I'll just put a bracket here. U minus 1/3 u cubed. And then I'll have plus some constant out here. And at this point, I replace u. So what's u?
Cosine.
Cosine of 4t. So that'll be my final answer. I forgot these markers are really hard to erase. Okay, so we have negative 1/4, I'll keep it in brackets, cosine of 4t, and then minus 1/3. And the way I'm going to write u cubed is cosine cubed with my cubed right there, 4t, and then close my brackets, and then plus some constant. And of course, you could distribute the negative 1/4 through, but I'll just leave it like that.
Do you prefer expanded?
I don't
Because
care.
you could also like factor out a cosine.
Yeah, you could factor out a cosine. No, it doesn't matter at this point, no. Just as long as you got it back in terms of cosine, we're good. Just don't leave it as u. Okay, what do you think?
Makes sense.
Make sense? Okay, so really the only part of this that's kind of new is the part where we recognize that this was an odd power, which means if we peel off one factor, it's going to leave us with an even power. And because it's an even power, I can use the Pythagorean identity. Once I do that, everything's just basic U substitution.
Except you're not making it u. You're saying that since the derivative of cosine is sine, that u is cosine, and du is set equal to sine.
Yeah, it's kind of like, I guess, when I'm pulling out the sine, I'm telling myself, hey, look, that means u is going to need to be cosine, right? So I'm going to have to turn that sine squared into something with cosine.
Yeah.
Yeah. All right, so now what I'm going to do is I'm going to bring those notes back up. Well, I thought I was. Here we go. There we go. So let me go back up to the notes here. And it said, okay, first strategy was if you have cosine to the n with n odd. Well, we didn't have cosine, right? We had sine. So let me go to part 2. All right, if you have sine to the n with n being odd, we use a Pythagorean identity. And we factor out a single sine, which leaves us with an even power of sine, right? That's what happened. Now we rewrite the remaining even power of sine using sine squared x equals 1 minus cosine squared x. And then we'll let u be the cosine x, and then we use substitution. That's the technique, right? Now I believe that this sheet here, if I'm not mistaken, is in your formula sheets. Can somebody correct me if I'm wrong? I believe that you're allowed to print this out and take this to the exam.
What part is?
That right there? Yep. This is basically, it's a different sort of summary, but it says the same thing.
Where is that?
In the class files under formulas you can bring to the exams. Yep.
I didn't see that.
Yeah. So it's in there. All right. Okay, so let's go to the next one. Let's go to the next one. It's going to be integral sine squared x cosine to the 5th x dx. Now again, I'm not going to give you the strategy. I'm just going to do the problem, then we'll talk about the strategy. So in the last problem, we had sine to an odd power, so we pulled a sine out, right? That way we could get a sine squared and rewrite it as 1 minus cosine squared. Here we have sine that it's an even power right now, isn't it? So if we pull a sine off, we're going to be left with an odd power of sine, which we cannot use the Pythagorean identity. Do you all understand that? The Pythagorean identity says sine squared. So if you have a sine, you can't use it. So I don't think it's going to work for us to pull out or factor a sine out. Now we have cosine to the 5th, which means that we have an odd power of cosine. So if we pull off one of the cosines, we'll be left with an even power of cosine, which we can use a Pythagorean identity on, right? But if we pull off that cosine, what is my u going to need to be?
Sine.
It's going to need to be sine, right? So let's just take a look at this. I'm pulling off one factor of cosine because I had 5 factors of cosine. I'm going to peel off one factor of cosine, and that will leave me cosine to the 4th next to it. So I'm thinking ahead here that this right here is going to wind up being my du, right? Well, I might have a number in front of it, but it's going to be my du part, right? That's going to force my u to be sine, which means that I need to rewrite all of this in terms of sine. So this is already in terms of sine, right? But this is not, right? So I'm going to go back to my Pythagorean identities and remember that cosine squared x equals 1 minus sine squared x. Now be careful. because we don't have cosine squared. We have cosine to the fourth, right? Don't make this mistake. Cosine to the fourth x is not 1 minus sine to the fourth x. That is not the way that works, okay? Yes?
But cosine to the fourth x would be cosine squared x squared.
Yes, we could rewrite it as cosine squared squared, which is what we're going to do. So we're going to write sine x, then we're going to rewrite cosine to the fourth as cosine squared x squared, and then cosine x dx. So that's legitimate, right? That's a legal move there. And then I'll replace cosine squared x. Can y'all make sure y'all see that's not equal? Okay. All right, so now this is equal to sine squared x, and then I'm replacing cosine squared x with 1 minus sine squared x. Then that's squared, and then cosine x dx. There we go. We've got the derivative of sine here, right? And we've got just sines over here. So now let's make our basic u substitution. U is going to be sine x, because the derivative of that is cosine x dx. Now, in this problem, it would have been more complicated had I put like sine squared of like 3x or cosine of the fifth of 3x, because we'd have a little bit of chain rule here, right? But because it's just x in there, it's nice. The derivative is just right here, no scaling involved. So here's cosine x dx, that's right there. That's going to be du. And now I just replace all my sine x's with u's. So the new integral becomes integral u squared, parentheses, 1 minus u squared, quantity squared, and then this is du. And that kind of looks messy, but this is algebraic, and we can, what?
Yeah, you can square, you can, so 1 minus u squared, since that's squared, you just multiply 2 of those. So
Yeah, just expand this, right?
Expand it, yeah.
Expand this out. We're going to just expand that, and then we're going to distribute a u squared through. And then when we do that, we're just going to have a bunch of powers of u, and then we integrate with the power rule, and we're in business. Now, I'm not going to show the step of me actually expanding that. Just going to trust that you can square that and get that. And then I'm going to distribute the u squared through. So this is going to be integral. Then I have 3 terms. U squared minus 2u to the 4th plus u to the 6th du. And then I can do those one at a time. My shoes are falling apart. Better. All right, this is going to be equal to, let's see, 1/3 u cubed minus 2/5. My wife would be very upset with me if she knew I was wearing these shoes, because she's like, throw those away. Throw those away. She forced me to go to the store and buy 2 new pairs of shoes. So I went and did that. But then today I was like in a hurry, so I just grabbed them. All right, we ready? What do we do now? Just replace the u with sine, right? So I think this is probably the last problem that you're going to see me take all the way. From here on out, I'm just going to take it to a certain point, and then I'm going to say, hey, from here you could do it, right? And you'll say yes. Right? You understand? Because the problems are going to get longer, and we just don't have time to go all the way down to the answer. So like next time if I get to here or something, I'm just going to be like, okay, and then you could just expand that and then plug everything. You got it? Yes. And you'd be, yeah, sure, we got it. Okay. We go. We continue. So look, it seems like if we had sine by itself, odd to an odd power, we had a way of doing it, right? It looks like even if we had cosines and sines mixed together, as long as one of them was odd, we've been able to peel something off and then just use the Pythagorean identity, right? So that's pretty much the idea, the first strategy, is that if you've got sines and cosines, and one of them is odd, you're going to peel it off and then use Pythagorean. Now what if they're both even though, right? That's obviously going to be the next question. So we'll have to address that. But what if, okay, so let's imagine, what if this had both been odd? If that was sine cubed, right? If we would have done this, right, this would be cubed, and then that u squared we had up front would be u cubed. Big deal, right? We just expand it through. So it just would have brought up the powers on each of those. Now you could, if this was cubed, you could have also pulled the sine out, right? And turned the sine, let's say squared here, Pythagorean to cosine. And then you'd have like something with cosine here, and this would be cosine to the fifth, so that would turn out to be u to the fifth. So it'd still work.
Are we going to be expanding quite a bit of like higher powers?
I think the most you would have to expand is maybe a third power, like some binomial to the third. Yeah, I'm not going to push it any further than that. For an in-class test. Now on your homework you might have to go a little further, but on an in-class test you wouldn't have to expand anything more than a binomial cubed, just for time's sake.
How does Pascal's triangle work again? Do you not like that?
No, I do. I just don't have time for it right now. If you come by, or maybe if we have some time at the end, I can show it. All right. I would love to talk about it, just it's going to eat up too much time. So let me get through this stuff first, all right? Okay, so now let's take a look back up at the techniques. It said if we had cosine to an odd power, which we just had, we use Pythagorean identity, we factor out a single cosine this time, right, which leaves an even power of cosine, then we use this identity, let u be sine, and then use substitution. All right, so do those make a little more sense now that we've done two examples? Okay, now let's take a look at part C. Integral cosine to the fourth of beta t dt. All right, we're going to go right into the frying pan with this one, all right? Let's talk about why we cannot use the technique that we just used. Okay, so don't write this down. Let's just look at this. If we try and use this technique of peeling off one cosine, then this would force you to say to yourself, well, that means my u is going to need to be a sine, right? And then you try and turn this into a sine, and you can't, because it's an odd power. And there's not a way to rewrite that odd power as an even power. And it has to be an even power in order for you to use the Pythagorean identities, right? That makes sense? So, yes? No? Yeah? I see some people like that, and I see some people like this. Yes?
So you're only allowed to peel off one time?
Only allowed to peel off what?
One time?
You mean like peel off like a cosine squared, or?
Like you can do cosine squared and cosine and cosine.
Okay, so I do cosine squared and cosine squared, and then rewrite each of them as 1 minus sine squared? Is that what you're?
Yeah, or that, or if you could, I'm just trying to understand how many times you can peel off to separate it. Like you couldn't separate it to 4 single cosines.
You could, but the problem would be, what would you do with that? So let's say we have it. Let me just do x, so I don't have to write beta t over and over.
Aren't you only supposed to peel off if it's an odd?
Yes, so if it's an odd, yes, but I'm trying to get us to see why. So if I broke it up into 4 cosines, you cannot integrate them individually, right? Because that's a big no-no, right?
You just do like cosine squared bt squared?
Cosine what?
Like square the whole thing, just cosine squared. Cosine squared.
Squared squared?
Yeah.
Like this? I can do that, but then what do you do with this?
Pythagorean identity and expand and let sine.
Oh, cosine squared squared. Okay, so cosine squared squared. Okay, I think we're all getting to the same place, but let me do that. Okay, so what if I did that? If I did that, don't write any of this down. If I did that, then this would be 1 minus sine squared beta t that squared dt, right? And if I expand that, I get 1 minus 2 sine squared beta t plus sine to the 4th beta t. Do you agree that would be the squaring of that? dt? Okay, so this you could integrate. Antiderivative of 1 with respect to t is just t. But what are you going to do with sine squared? Turn it back into 1 minus cosine squared? Then what are you going to do with cosine squared? Right? You're still stuck. And then what are you going to do with sine to the 4th? Because it's still even, right? Just have not been able to get rid of that even power. So this, I would argue, is even more complicated looking than cosine to the 4th, right? It's all this crap and sine to the 4th. So we're still stuck. Does that kind of... So play with it all you want. It's not going to happen, which means we need something else, right? We need a different sort of way to go about it. And it turns out all we need is a different formula. We were using Pythagorean identity, weren't we? But there's a few other in pre-cal that were pretty useful. And there's one in particular that's very useful. And it's the formula sheet calls it something. You can look it up. I call it the power reducing formula. I'm not the only one who calls it that. Other books use this instead. The power reducing formula. Let me write it down, and then you'll see there's two of them. First one is sine squared x equals 1 minus cosine 2x over 2, and the other one is cosine squared x equals 1 plus cosine 2x over 2. Now, these formulas may or may not look familiar to you, but these are from pre-cal. And they call them half-angle formulas on your formula sheet, right? I believe they're on the bottom right. Okay? They call them half-angle formulas. I don't like that name, half-angle. I know why they use that name, but I like the power-reducing name instead, because what does this formula actually do? It reduces the power. You go from a sine squared to a cosine, right? You go from a cosine squared to a cosine. This is not a typo. They're both cosines. This one's minus, this one's plus. But there's a give and a take for it. This formula allows you to reduce the power on sine, but to do that, you're going to have to double the angle. So whatever argument was in here gets doubled. Yes, you can reduce the power on cosine, but you're going to wind up doubling the argument. Okay? Yeah, power reducing argument doubling. Now, I don't like this form of the formula. In pre-cal, that was fine. But in Cal 2, it's better if we write that formula 1/2 1 minus cosine 2x, and then this one as 1/2 1 plus cosine 2x. And that's just because we're integrating here. And so if we can factor out the 1/2, sorry, then that can just come out of the integral, and we don't have to deal with it. So it's just easier to work with. Okay, so you'll see me using this is equal to that, and you'll see me using this is equal to that. So when we have an even power of sine or cosine, we're going to go to one of these formulas. So let's see how this would work. Now, unfortunately, we still are going to have to write this as cosine squared beta t squared. So that first step is correct. We need to look at that as squared squared. All right? But the cosine squared beta t in here, we're going to power reduce using this formula. So this is going to become integral, and be real careful with your parentheses here. We're squaring whatever that becomes, right? Now, what does it become? 1/2. Yep. Okay, so 1/2 parentheses 1 plus cosine 2 beta t. 2 beta t. And then that whole thing gets squared. Are y'all good up to that point, though? Yes? I'm missing a parentheses. That 1/2's out here, and then it's all of this. There's my parentheses here, and then all that squared. So how about we do this?
Can you move that 1/2?
Yeah, let's get the 1/2 out. So we understand that that's multiplication between two things that are both being squared, so we can square each one, right? So when I square that, it's 1/4, and I'm going to just pop that out of the integral. think I'm going to move up here. 1/4 integral. Now I'm still sitting here at 1 plus cosine of 2 beta t, that quantity squared dt. So I haven't squared that yet. You cannot do anything like a basic U substitution right now. You can't. You cannot just integrate these individually. Why? Because it's being squared, right? So our only option is to square it. We actually have to multiply that times itself, which means we have to FOIL. So this becomes 1/4 integral. Let me just let you know. When you see cosine or sine to even powers, be ready to do some work. It's just going to take you a while, all right? These are kind of tedious. All right, so now I expand. When I expand that, I get 1 plus 2 cosine of 2 beta t plus cosine squared of 2 beta t, and then all of that dt. Okay, is that all right? You see how we do that? Just this times itself, FOIL it out, you get 1, then collect like terms. Is that all right? You sure?
Yeah.
Okay. Now can we do them individually? Yes, because they're not being squared anymore. So what's the antiderivative of 1 here? T, all right, because that's that. Can you take the antiderivative of cosine of a linear expression? Yes. We're going to have to do like a 1 over a thing here, right? Can you do a squared? It's squared though, right? So what? We got to do that formula again for this one. We got to power reduce that one again. See that? This is your life, okay? This is your reality right now, okay? This is what you have signed up for. Okay, so look, I'm going to break this into 3 integrals. I'm allowed to break this into 3 integrals. Now, I normally in the past have not broken it up into 3 integrals because we really haven't needed to, because what we would do is we would just get it to a point where we could just do them all at the same time. But right now, I can only do a few of them right now. So I'm going to do this one. Notice I brought the 1/4 and then this one, and then I'm going to do that one. This one I'm going to have to do some work on, right? But let's take care of these first ones. So what do I get there in that first integral? 1/4 t? Okay, plus, now we've got some constants here. I'm going to have a 1/4. I'm going to bring that 2 out. And then when I take the antiderivative of cosine of 2 beta t, 1 over 2 beta, right? Because a is the 2 beta. And then sine of beta t, like that. 2 beta t, sorry, 2 beta t. 2 beta t. I'm done with that. I'll have a plus c, but I'll just throw that in at the very end, okay? And then I still have to do this integral over here. 1/4 integral. Now, because it's cosine squared, I can use my formula, right? And the formula is that this becomes 1/2. Then, what is it again? 1 plus cosine of double the angle.
It's 4.
4 beta t. Putting it in blue here because it's important that you understand that this thing right here got doubled. In the formula, the argument gets doubled. So if it's 2 beta t, it becomes 4 beta t. Okay? All right, let's go back up here. We need some more room. All right, so here we are. We have that this equals 1/4 t. What winds up happening here? 1/4? Those 2's cancel, right? So these 2's cancel. And we just get 1/4 of sine of 2 beta t. I forgot my beta down there. 1/4 beta. Thank you. Lost that guy. I don't know why I did that. 1/4 beta. Sine of 2 beta t. And then plus, let's just go ahead and bring the 1/8 out. Plus 1/8 integral. And then 1 plus cosine of 4 beta t dt. Right? Forgot my parentheses. Keep doing that. Okay. Now, can we integrate each of those individually? Yes. Because I don't have a power there anymore. So 1/4 t plus 1/4 beta sine 2 beta t plus 1/8. Okay, here we go. Antiderivative, I'm just going to put it in brackets here. Antiderivative of 1 is just going to be t. And then the antiderivative of cosine of 4 beta t, 1/4 beta, sine of 4 beta t, close my brackets off, plus c. And then we could distribute the 1/8 through, right? And I'm going to, because there's one more little simplification we can do. I don't know if you see it right now, but you see how I have a 1/4 t out here? And when I distribute the 1/8 through, I get a 1/8 t, and those are common or like terms, and I can put those two together. So when I distribute the 1/8 through, I'm going to cheat. Do you agree I get 1/8 t? And do you agree when I multiply the 1/8 here, get 1/32 beta? And then I don't need that anymore. And then group these two together, combine those. 1/4 plus 1/8 is 3/8 t. There you go. That's the antiderivative of cosine to the 4th beta t.
So if we had like cosine 4th times sine to the 6th, so like 2 even powers is going to be like a lot of work.
Yeah, that's actually kind of torture. In fact, if you just go home and do your homework, I believe, if I'm not mistaken, there is like a sine to the 6th or a cosine to the 6th in the homework. So you wind up having to do like, let's say sine to the 6th, x. You wind up having to rewrite that as sine squared cubed. And then when you use the formula, it's 1/2, 1 minus cosine 2x. But then all of that gets cubed. So you cube the 1/2, it's a 1/8 goes out, but then you have to cube this. And when you cube that, it's a monster. And some of those pieces in there have to do the formula again. And then when you do that, you actually have some pieces in there that are odd powers of cosine, which means you have to use what we learned before this. So sine to the 6th or cosine 6 is a true torture problem, but I believe it's in the homework and it's something that I remember suffering through in Cal 2. I think I had to write it down sideways on my paper. I couldn't get it this way. I had to like write like this because it just, the lines became so long. But, you know, like I said, I'm the messenger here, okay? Remember what I said in the beginning of class when I talked about this section is broken up into 2 parts. Next class, we're going to be doing problems that what we're going to do is we're going to be like working, we're going to get it, and we're going to go, cosine the 4th, good, you can take it from there. You know what I'm saying? Like that's where we are. So on the next test, give you a problem, and in that one problem, it's going to have what we do next time, it's going to have this, and then to do this, there's obviously U substitution in here, right? So it's like one problem covers like 3 different techniques of integration. Yeah, it's very fun. It's very fun. Yeah, there's not many problems on the second test. Yeah. There's 2. There's 2 problems. Yeah, exactly. Okay, so let's take a look at that second technique. That if you have sine or cosine with an even power on one of them, or look, if you've got odd powers, you should be happy. All right, because odd powers, you just peel one off, use Pythagorean identity. But if you have nothing but even powers, take a deep breath, stretch your hands out, maybe go get a drink, sit down. You're going to have to spend some time, most likely. All right. If you have even powers, be prepared to use the formulas for the power reducing, half angle, it was right here, half angle, or the power reducing formulas. All right, so we did those 3, right? Okay, let's move on. Let's move on. How about integrals involving tangent and secant? So think about this. When we did the odd powers of sine and cosine, we were using the fact that if we peeled off a cosine, then we could let u be sine, right? And if we peeled off a sine, we could let u be cosine. And it worked when we had odd powers of sine and cosine. Now this, we needed a power reducing formula. But with tangent and secant, it doesn't work that way, right? The derivative of tangent is not secant. And the derivative of secant is not tangent. The derivative of tangent is secant squared. And derivative of secant is secant x tangent x. So with secants and tangents, it's not going to be as easy as just peeling off a secant or peeling off a tangent. What are we going to have to peel off instead? Either a secant squared or a secant x tangent x. That's what's going to have to get peeled off. And then we have to use a Pythagorean identity. Now, do you remember the Pythagorean identities for, well, everyone remembered this one. Well, I don't know if you remembered it. I hoped you did. But do you remember that there's 3 others? Or 2 others, sorry, 3 total? Yeah, so you either divide everything by sine or you divide everything by cosine squared. So if I divide everything here by sine squared, what would I get? Divide that by sine squared, 1. Divide that by sine squared, you get cotangent squared. And then divide that by sine squared, you get 1 over sine, which is cosecant squared x. So that's one of the other Pythagorean identities. Then you could take the same equation here, divide everything by cosine squared to get the last one. So this one divided by cosine squared, tangent squared. This divided by cosine squared, 1. And then 1 over cosine is secant, but then squared. So those are your 3 Pythagorean identities. We've already used the first one. We're going to start using this one now because it has secant and tangent in it.
Appreciate it.
Okay, so let's see. Do we read through the techniques first? No. Let's see. We know that the antiderivative of secant squared is tangent. We know that the antiderivative of secant x tangent x is secant x. That we know from Cal 1. We also can extend what we learned already, that if you have a linear expression inside, you're going to have to scale it. So if you were to take the antiderivative of secant squared of, let's say, 4x, you're going to have to go 1/4 tangent 4x. If you have secant 10x, tangent 10x, you're going to have to go 1/10 secant 10x to take care of that 10 in the chain rule. Right? That's just extending on what we've already talked about with sine and cosine. So strategy, blah, 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 blah. Okay, let's do this one. Tangent to the 4th x, secant to the 4th x dx. So do you understand that if those were sines and cosines, we would be very upset right now? Okay, but they're not. And the fact that we've got even powers with tangent and secant is a little different, because we know that secant squared is the derivative of tangent, right? Secant squared is the derivative of tangent. So right now, because I have a secant to the 4th, can't I peel out a secant squared? And I'd be left with what still? Still a secant squared. So I'd have two secant squared side by side, right? What could I do with that first secant squared? Okay, so I peel one off. Here's a secant squared. What do I do with that other secant squared? Pythagorean identity, right? Rewrite it in terms of tangent. And the derivative of tangent is secant squared. So it's kind of like what we did with the cosine and the sine, but because the derivatives are a little different here, we're going to peel off actually two factors. So I'm going to peel off a secant squared x, okay, right there. And that part I know is going to be my du. So that's going to force my hand here. I'm going to do a u sub here. I'm going to let u be what? Tangent x, just tan x. The derivative of that is secant squared x dx, which I have exactly. I'm very, very happy to